So this is Dr. John Archer, and he heads up the forage analysis of forage at AFBI Hillsborough for us. So he is definitely the expert in the room when it comes to forage analysis.
Let's hear about that.
So he's kindly agreed to give us a bit of a presentation, just going through understanding the results and where the values are coming from.
Yep.
So,
hopefully, and then if you have any further questions, I can hopefully answer a few.
Yeah, we've got a nice small group. So are you happy to take questions as we go through, or do you want to leave them to the end? Or?
I don't mind if somebody wants to interject. That's very much 100%. It's not terribly complicated. It'll flow, and then better questions at the end. Or if somebody is itching to ask a question, certainly jump in. No issues at all. So.
Well, yeah, I'll hand over to you, John.
Okay. Well. Yes, I'm John Archer. I work at AFBI Hillsborough Lab, and I'm going to try and share a screen with you, and I hope it works because, of course, we're relying on technology. So hopefully that will be the case. Just bear with me. Can everybody see that?
That's come up, yeah.
Okay. So grass analysis by near-infrared reflectance spectroscopy. I'm just going to give a wee bit of an introduction, and then I'm going to go through the different parameters and an aspect of what way that analysis pans out. It shouldn't take more than 10 minutes, so apologies if it's too simple. And if there's any more detailed questions, please ask, or we can refer to it at the end of the PowerPoint presentation. So yeah, grass analysis, or fresh grass analysis at NIRS, using NIRS, has been carried out at Hillsborough for quite a long time, possibly the last 15 years. We've developed various different equations. And one of the big things would have been our silage analysis, which goes back maybe 20 years. And you may know that part of the FAA group, Forage Analytical Assurance Group, we have been using near infrared for quite a long time. So there's a fair bit of expertise in near infrared. I'm just giving you a quick diagrammatic of what way near infrared works. This is a spectrometer on the left-hand side, and basically just a small schematic diagram of how it works. And you're just simply shining light onto a sample, and the amount of light that's detected is relative to the amount that's absorbed by the sample. So you end up with a spectrograph. And without really getting into the boring bit, you end up doing a thing called chemometrics, and chemometrics is where you marry the two together. You take effectively the spectral graph, and you take what's called reference chemistry, and you create a calibration. So I'm not going to go into that. I could spend 3 hours at that. So the whole process gives us a report. When we scan the grass, we end up with a series of different analytical parameters, and hopefully we get a report something similar to this. And this is just happens to be the AFBI Hillsborough one, but you do get different types of parameters or different layouts of results. But it's all based on the straightforward quality parameters that you find possibly in your silage report, but also in this case in fresh grass. And of course, it's bespoke. It's very, very unique to the fresh grass that we're working with in the GrassCheck. So we're going to be considering things like the dry matter, the crude protein, the ADF, or acid detergent fiber, water soluble sugars, and ME, or metabolizable energy. So what does that really mean, and where do we get the figures from, and how does that relate to week on week, month on month, according to analysis is concerned? If you want to interrupt, that's 100%. So just a small or quick explanation of the terms before we go any further. So basically dry matter, and I really, people think dry matter and think, this is an easy thing. Well, it's actually a lot more complicated than people think. But basically, it's that material that hasn't got water in it. So it's the amount of material that is left after the water has been removed. And for a lot of people, that sounds simple, but for a lot of people, it's hard to get their head around. So if you have a ton of material, which is 1,000 kilograms, 30% dry matter, that's 300 kilograms of dry matter. That's just the way I look at it. So it's expressed as a percentage of the actual fresh material. And then the dry matter increases slowly as the maturity of the grass increases. So obviously, any grasses in and around before May, you'll see there in the graph, it progresses up to crescendo and then falls back again. Now, this would be grass that's grazed or, simulated grazing as far as research is concerned. So you have that potential for the dry matters to increase. And I've just given a general graph. That's not, different swards, different management systems, it all changes relative, and we're in the real world as well, and we're talking about a wet spring, so that'll have a different effect on the relative amount of dry matter in grass. But so you can get grasses that when they're mature, you're getting to a point where the dry matters can actually reach to higher than 30%. But of course, that's maybe, you're getting into something like hay or something that's very stemmy. So going on to the next parameter, we're all familiar with protein, or in our case, crude protein. The reference chemistry has been done for years. There's a process called Kjeldahl nitrogen analysis. I don't expect everybody to know that, but the point is we have used that reference chemistry to calibrate our instrument. And that reference chemistry relates to crude protein in the dry matter. And of course, if you have your 30% dry matter and then you've got something like 25% or whatever it is as far as the actual crude protein is concerned, it's all relative to the dry matter. So let's consider the fact that, as we've seen, the dry matter increases through the year in a grazed sward. But then in a scenario where you have actually different forms of grass, different scenarios, different management systems, the protein as a whole tends to drop. So at this time of year, you tend to be at the highest level of protein in grass. And as I say, during May, crude protein values can be greater than or equal to 25% dry matter, but can drop quickly. And you have the worst case scenario, or the extreme in hay or haylage, where the crude protein can go down to less than or around 10%. So that's crude protein. Soluble sugars, again, it's the sugar on top of your Weetabix scenario as far as parameters is concerned. It's that sugar that's soluble. But how does it work? How does it affect the plant, and what way does it affect us as farmers, stroke producers, trying to use the grass? So is mainly the glucose, fructose, sucrose, and fructans in sugars. As I say, they're soluble, they're easily dissolved in water, they're obviously movable within the plant. These sugars are the fermentable substrate for the production of lactic acid, which is the main preservative in grass silage. So again, with different management systems as far as grass is concerned, grazed grass, silage grass. But in the case of sugars, they are the primary stage of what happens in photosynthesis. And people forget that, what is actually photosynthesis? Again, I'm not, everybody knows this hopefully, but in effect, carbon dioxide and water plus sunlight produces sugar and oxygen. But the irony of it is, if you lose out in one or two of those things, then that stunts the growth, because the actual production of sugar is restricted. So the environmental factors affecting these parameters affects the rate of photosynthesis. There's a water stress and poor sunlight conditions, slow or stop sugar production in the plant. It sort of stands to reason if you don't put the parameters in it, or the water and the carbon dioxide in it at the initial stages, and have nice sunlight, you certainly won't have any growth. And we all know that as far as the general growth of grass. But it's that biodynamic that we're really considering here, because we actually need the three parts of the equation to give us some form of growth. And we forget that grass is a plant, and even though cattle have been grazing it for hundreds, thousands of years, the key point is it still needs the sunlight, it still needs the water, and it still needs carbon dioxide ironically, to keep it growing. So if we lose out on any of those, we don't get much growth. Again, it tends to peak during mid-afternoon and then on an average summer's day. And the parameter in itself, normal range is sugars is between 8 and 20%. Dry matter with between 1 and 5% of the fresh material. So it depends. Some reports will give you it in the dry matter. Some reports will give you it in the actual fresh or grazed grass type, just to depend on the way you're actually reviewing the data. So be careful of what you're looking at, because if you're getting grass ready for a silo, it's probably in the fresh. So again, that's the sugars, generally around 2.5% is required for fermentation. So again, that's just a simple overview of the way, a general projection of the way grass sugars go through a season. ME, again, metabolizable energy. It does what it says on the tin scenario, a measure of the available energy to ruminants. We're very much focused on ruminants as far as grass is concerned, but of course, there's other animals will eat grass as well and gain energy from it. But we're just going to simply review ruminants at the moment, cattle, sheep, and when we consider ME, we consider really the D value, or the digestibility figure. And there's a lot of what is D value, what is ME. I'm not going to go into that too much, but basically the general digestibility of grass and the level of maturity of grass has an effect on what the animal can get from the actual material itself. So early grass will have an ME of around 12 with a D value around 75. As grasses start to go into flag leaf, and we talk about earlies, intermediates and lates, in mid-May the ME will drop to about 11 with an equivalent D value around 69. And then if it goes a very extreme, and just to know your full range of your ME relative to your D value, you can actually, if you think about it, hay can actually go to an ME of around 8.5 with a D value around 53. So you can see the two things are really interlinked. But the key point for me is, if you look at the two graphs, you can see a general progressively, a downturn as far as ME is concerned, relative to the grazed grass scenario. But you can also see, depending on how you manage your system, and sheep farmers, dairy farmers, suckler cattle, all rely on a good healthy level of digestibility within the sward, so that you can keep the energy levels up in the animals. But you can see a dip there as far as D value is concerned, and that will change relative to the amount of maturity you allow your grass sward to get to. Don't want to bore you with it, but basically it allows you to monitor and be able to try and encourage a system where you're trying to keep the D value as high as possible. And then the other side of the coin, as far as ADF is concerned, so acid detergent fiber is basically the structural carbohydrate of the plant. Cellulose and lignin. Your trees have lignin in it, just the same. And Arnium ironies, we've tried to saw trees up, and we need chainsaws to do that. It's the same in the animal's stomach. You need to have an ability to break down the food materials, and of course these are the fibers that won't break down. That's what's left after it goes through the digestion process. The ADF is really an important parameter, because you will end up with what is effectively why you have high levels of fiber whenever you allow grasses to get into a flag leaf scenario. And of course, if you've grazed grass with sheep, you don't want to allow them to get into a strong sward, because first of all, from my experience personally, they tend to ignore it unless they're pushed into it. So they like the nice leafy grazed, easily digested grass. Cattle will be a lot more resilient and want to eat. But the more flag leaf, the more the higher the level of ADF, or acid detergent fiber, in the grass. So just to say, my experiences with grasses and ryegrass, Lolium perenni, and inflorescence the way they define it according to varieties is concerned is between, early May. You'll see inflorescence with an early variety. Intermediates tend to be between the mid-May to late May. So from my thinking would be from about the 20th of May through to the end of May. That's when you'll see the intermediates starting to flag leaf, emergent as we call it. And then the late varieties, they start from early June or very, very last day in May through to about the 16th of June. So depending on your sward, depending on your management system, depending on the amount of moisture you're hoping to get through the season, that will dictate what type of grasses or grass swards that you want to have. And you can see there that that rises just in the graph. It rises quite considerably as the maturity of the grass increases. And that is, again, looking at a grade sward, grade sward management system, but there's still that flag leaf trying to push through because there is a thing called secondary heading. And as the primary heading, you can cut your sward and have it nicely cut with the first cut. But guess what? There's a secondary heading coming around the corner, and that's why second cuts tend to be in your silage sward anyway, that wee bit less digestible because you've got a lot more ADF in it. So moving on, there's two other parameters I want to talk about, and I just don't want to bore you too much, but I want to just give you an overview of what the difference is in fresh graph analysis at Hillsborough anyway. We describe grass as far as what grass monitoring or fresh grass for grazing, but there's also the ensilability aspect, and the two aspects that I want to focus on in this case is just simply the nitrate and the buffering capacity. Now, why do we do that? Because if I just move on to the next slide, the nitrate is effectively the fertilizer that hasn't been used. So if you have poor transpiration, the soil may still have the fertilizer in it, and then suddenly you have a period of rain and the transpiration increases within the plant and the nutrients move up through it. So you still need to have time to review how much nitrate is actually not being processed by the plant so that it can actually create protein. So this is just simple biology really, but in effect it's very important, especially if you're making silage, or in the case of folks wanting to graze grass. Again, it can be quite bitter. Fresh grass at a very high nitrate level can be quite bitter for cattle because of the level of nitrate, and it doesn't help them. So that wee bit of encouragement to allow grass to get that slightly more mature, but also not go overcook it as well. There's always a purple spot in the whole thing, and you know your own system. So so just to read it out: immature leaves with a nitrate level of greater than 66,000 parts per million fresh. This reduces the active growth, and the high levels of nitrate led to poor fermentation and silage production and can affect rumination in a grazing situation. Less than 10% ppm is adequate for good grazing, and that tends to be, and I'm sure you've heard about the grazing wedge, and again it's all relative to how much nitrate's been used up by the plants, and again the amount of protein relative to that. So all of these things are interlinked, and again nitrate, protein production within the plant, digestibility, ME, energy for the animal. It's all sort of all part of a bigger picture. So we're trying to just basically simply suggest that all these parameters have importance, not just in the actual report, just as a piece of data for to look at, but actually from an application point of view. And then there's a last parameter which is called buffering capacity. And to understand that, it's just basically the ability for grass to resist pH and change. And it's very much according to ensilability, but really the soluble sugars ferment to form primary lactic acid and acts to lower the pH in the ensiling process. So it's very important to have a certain amount of sugars and also an ability to be able to change the pH quickly in the silo. And in some cases we use additives. In some cases the actual grass will do it naturally. Depending on where you are in your grass sward, how clean, how new your sward is, the less resistance you have and the lower the buffering capacity. So high BC will have over 500, it's called milliequivalents per kilogram dry matter, and that will slow the grass fermentation process in the making of the actual silage. And in grass, fresh grass with high BC, again, it's hard for the animals to effectively digest that because of the resistance to pH change. So that's my seminar finished. Hopefully I haven't left anything out, or maybe you have some questions.
Everybody's nice and quiet.
I've knocked you over to sleep. I'm sorry about that.
Can I ask, dry matter, is that calculated with the light shiny thing, or is that calculated by drying it? How do you work it out?
The initial analysis is carried out reference chemistry, but we're simply scanning it now at this stage. We created the reference data for the spectrometer, and now dry matters are determined through spectroscopy using the near infrared.
And how accurate do you think these things are as a reflection? Because I always struggle to get the same value out of any silage whatever I analyze compared to these things.
And we find it, we actually have a quality assurance aspect to our analysis, and we have to present that to ISO accreditation people. We find that there's about a 2 to 5% of an error factor in the figure. So that's not to say it's 2% in the figure, is 2% of an error factor. But as a whole, dry matter is the one parameter that we're very, very confident with an R-squared value or a correlation value over 0.9, and 1 being perfect, with a slope of very close to 1 as well. So we've been very particular at Hillsborough to align dry matter with the reference chemistry. And I suppose I'm maybe more of a fusspot than a lot. I suppose it's my job really, but spectrometers are notoriously, they will drift. So this is where I would suggest that reference chemistry has to allow to some extent the drift of instruments. But I'm very happy with dry matter and crude protein prediction according to near infrared. But we have to hold our hands up, and there's nothing to beat the effect of using an oven. But the whole point of the scanning process is to allow us to have a rapid analytical process, and with an accuracy level of over 0.9 of an R-squared value for the dry matter, I certainly am very happy with that, and would encourage people that that's definitely the way to go. The big problem with a lot of people is that first of all, the use of the instrument, and also how particular they are in the way they generate their their reports. So I mean, in our system in the lab at Hillsborough, we have a training process, and you don't get onto the system unless you have actually been trained properly. Second thing would be that the instrument is properly maintained and serviced. So a lot of those things go away, go by the by, as it were, if people are maybe running around with a hand scanner or something. But you shouldn't, put it this way, you should always get a good dry matter accuracy. If you don't get that, if you consider all the different parameters relating to that, I mean, all those different other things like crude protein in the dry matter, ADF in the dry matter, those all relate to the dry matter. So if you have pure dry matter prediction, you're ending up with a poor report in general.
Yeah. And are you cross-referencing with other labs as well?
Yeah, well, as I say, we're part of what's called the Forage Analytical Assurance Group, and our spectrometers are being, well, we have the master instrument. I suppose we have the luxury of that because of having done the research in the past, and having done a lot of the reference chemistry, with the high, medium, and low volume values for the different parameters. So there's quite a big database, and there's also quite a big volume of range within the analysis for the NIRS process, which makes it robust. So yes, we're part of what's called the FAA group, and then we have our own internal what's called IQC and EQA analysis, which if you're in a laboratory environment, you'll understand that you have to have your internal standards, and you also have to have your external standards to align with. So yeah, there's quite a bit of analysis.
So,
oh, yeah.
So obviously the samples that come from GrassCheckGB aren't going through the Hillsborough lab because we have Scientech on board as a sponsor and as a partner, and partly because of the logistics of posting all of the samples and the delays sometimes we see. But Scientech are in that FAA group as well, and they adhere to the same assurance standards.
Yes, and we would help them as far as their quality assurance is concerned. So what I mean by that is that we would have cooperation directly with them, but not only that, we would also be, as I say, if they have any issues or scenarios going on, we would try and troubleshoot them for them. So we're very much in the background trying to keep everything correct.
I think going back to Jonathan's point about if I caught it correctly about, you get your analysis and you don't necessarily see the same feed out from the silage. I mean, there's a whole load of factors that could be influencing that, and I'm probably not going to remember them all, but it is difficult, and I'm not suggesting that it's in your sampling, Jonathan, but it is difficult, I think, when you're sampling in the real world, taking samples across a paddock or across a bale and trying to get a representative sample to the laboratory of exactly what you're going to be feeding, because there is that natural variation through a bale and through a paddock, and particularly through a clamp. The laboratory analysis might well be very reliable of what's been received, but it might not be completely reflective of what you. So there's always going to be that slight margin of error just in that process as well.
Yeah, I would agree.
I have a question, if that's okay, regarding ADF. You're saying obviously if it's too high, there's problems with that. But what can it be too low in terms of fibre, and kind of where's the sweet spot for that? And is it different for different types of animals?
Absolutely. I'm of a believer that well, my focus is generally silages, but the general review of ADF is not just grass in an ensiled environment, but also fresh grass. And it's reciprocal of what is effectively your digestibility figure, or your D value. If you want rule of thumb, you could subtract your ADF from 100 and more or less get a D value. It's what the animal would affect. In a rumination scenario, the animal needs a certain amount of fiber to be able to churn the stomach, as it were, and the bugs or the bacteria in the bacterial flora of the actual rumen are needing some fiber. To have a very poor fiber content or a very, very highly digestible grass can be counterproductive in one sense as well. I mean, there is, as you say, a sweet spot. Now, a dairy cow relative to a sheep or relative to other ruminants is very different. And so it's not something I can actually say, yes, the 20% ADF is the ideal, or 25 or 27. I would suggest that it's more according to, what is your management system? How productive are you wanting your animals to be? Is it relative to the stage that they're in their lactation? Is there an aspect of post-parturition as far as lambing is concerned and the ability to produce milk? Is there a scenario where you don't want to have over fattening or under conditioned ewes just pre-lambing? I think it nearly stands to reason that if you have a very high ADF, you just have a low level of energy. So again, we're working with, you know, less hay and more in, you know, in high quality silage. But you can have a very high quality, high ME silage, and it'll not really do them much good either, because yes, there's nice level of energy, but the fiber level is so low that you need to actually add straw. So there's a combination of those things. So this is where a nutritionist would be the person to ask, really. But my mind would be that there is a certain amount of fiber necessary, just like we need our fiber, so does the animals.
And you'll see it in, so it'll affect the passage rate through the rumen. So if there's not enough physical material to be held in there to be digested, it flows through very quickly. So you'll see it in the feces, and you'll see that whilst you might be putting it in a very high quality feed, the animal won't have time to get the best out of it because it will run through them a bit too quickly.
Yep.
Any more hands up? Andrew, did you?
Yes, yeah, just a quick one on gut buffering capacity. Do you
Yep.
see a lot of difference between different varieties of grass, or types of grass? You know, say, you know, the ryegrasses to clovers to
Well, my experience is really just ryegrass, because I was in a breeding program for 25 years breeding ryegrass. The key point for me is that buffering capacity according to a sward can vary quite a bit, and the more you let it get to maturity, the higher the BC factor. The big thing is to not let it get too high. It's very important as far as ensiling is concerned. Animals will nearly tell you that when you put them into a very heavy sward or, you know, strong grass, they'll go to the sweet grass first, and they'll ignore. They in their own right will want to have a lower BC, but it's not really variety orientated. I mean, you could have Timothy type grasses, you could have your Italians, your different types of ryegrass, whatever. It's more effectively the level of relative fiber and the overall digestibility within the grass, and which relates to what is effectively the animal's ability to metabolize that, and make the nutrients available. The acid change in the rumen is really what you're actually, or in the silo is where this is really a big thing, because, you know, we did mention the sugars. That's the kickstart for the bacteria. The bacteria want to get the pH down to the low level, you know, where lactic acid begins to stabilize the whole fermentation process. If you have a poor grass quality going into the silo, you will then end up with a poor level of fermentation. The buffering capacity is resisted. So in other words, your ability to change pH from around 6 down to about 4.5 is difficult, or 4 even in a good silage. So that's what I'm really trying to estimate there as far as BC is concerned.
Okay, thank you.
Anybody else? I might. We're going to try. John, I think I need you to stop sharing before I can share.
No, yes, no problem. Thank you.
I'm going to start my presentation with the caveat that I am absolutely not a nutritionist, but I'm going to do my best to run through how. So John's run through the main parameters, and I'm just going to talk about how, when I can get it sharing properly, how those relate to animal requirements for maintenance and obviously mainly for production. Has that come up okay?
Yeah.
So the primary thing that we're going to be looking at in terms of intake is the dry matter values that John's been talking through. The dry matter intake potential of your stock is going to be influenced by a number of different things. So lactation and stage of pregnancy, in particular, the physical space that pregnancy takes up in the animal can limit the space for the rumen, so we tend to see a reduction in dry matter intake in late stage of pregnancy. But we also see dry matter intake being influenced by animal requirements in terms of stage of growth and their age, and what their production demands are. And body weight, so the physical size of an animal, has an impact on their required dry matter intake for maintenance and for production. And we do tend to estimate, so body weight is a nice figure to estimate or to predict a rough and ready idea of dry matter intake for an individual animal from. As John said already, the dry matter percentage of grass is dictated by sort of the climate conditions at the time of grazing and by the sward's physiology in terms of maturity and those kind of factors. So we certainly can't control the climate. We can influence some of those sward physical characteristics with the management. So, you know, I'm preaching to the choir here in terms of the group of farmers that I'm talking to, but in terms of managing your residuals and maximising the leaf proportion, and minimizing the fibrous stem proportion, you're going to see higher energy and lower dry matter in the swards, sort of relatively. When we look at the climate conditions and we get very wet swards, we can see that low dry matter forages, so looking at some figures, probably talking sort of below 12 or 13%, which thankfully we don't see too often, but after sort of probably after the end of March, we will have had some very wet samples coming in. And when animals are consuming very low dry matter forage, it is going to limit their ability to meet their intake requirements. The volume of water that's being consumed at the same time takes up physical space and limits that appetite and that intake. Just been talking about fibre proportions and ADF. I've got some figures on NDF that came from NADIS. So just saying that, again, very high proportions of fibre can reduce an animal's voluntary dry matter intake as well. And it's putting figures for high yielding dairy cows that if your overall diet has an NDF of over 55%, or if your forage is over 25%, that's the level at which you tend to see a reduction in voluntary dry matter intake in response to the fibre portion of the diet. So there are various figures and various calculations for estimating what the dry matter intake of your particular stock group are going to be, and I will circulate, or certainly if people are interested, I can circulate these slides. These are some figures from the AHDB for beef cattle at various stages of production, the proportion of body weight you would be allocating for dry matter intake, and the same for different classes of sheep and for growing lambs. Similarly, for dairy cows, this table's come from the MSD veterinary manual, varying by production and by stage of lactation or animal age. This is sort of dry matter intake for individual animals over a 24-hour period. So this is the total amount of feed that they're going to need to take in to meet their production requirements. What we see, the beef and sheep systems, it's very easy to meet production from grass through most of the year. The dairy cows, supplementation is pretty much a given. With the grazing studies that have happened at AFBI over the last sort of decade or so, they've done some average calculations, and we have estimates of the daily grass intake from our grazing herd, or from our spring calving grazing herd, as they progress through the season, and that's in the table on the right there, ranging from sort of 16 kilograms of dry matter in the peak of the grass growing season and at the peak of the lactation curve, dropping down to just 10 kilos in October. In terms of sort of meeting animal requirements, energy supply is probably really the key one that is the one that you'd want to focus on, certainly in the first instance, and just trying to make sure that you're meeting those basic requirements for energy. And the figures for those, as John's explained, it's metabolizable energy value, and that's given as a megajoules per kilogram of dry matter. Now, I did think, shall I talk to you all about protein and rationing for crude protein? And then I did my revision and remembered just how complicated protein rationing can be in ruminants. I think that's above and beyond the amount of time that we have allocated this afternoon. But just to highlight that protein requirements for ruminants are quite complex. So the crude protein that you're seeing in your forage analysis is not a reflection of true protein, and it doesn't necessarily give you an indication of protein quality, but it's giving you an indication of how much nitrogen assumed to be protein is in that forage sample. And what we're doing when we're feeding sheep and cattle primarily is we're actually feeding the rumen as much as we're feeding the animal. So microbial protein synthesis is an essential supply of protein to ruminant animals, and their demands specifically for proteins in their diet are very different to our demands as monogastrics. So it's estimated that microbial production of protein supplies around 50% of the amino acids which are taken up in the small intestine. So it can't be underestimated sort of how important that microbial population is, and the activity and the production of nutrition that comes just from that microbial community as well. So forages are analysed for crude protein, and what we can say quite comfortably is that the vast majority of the time when we're looking at grass samples, the crude protein supply for beef and sheep production in particular is going to be adequate for animal demands. And actually, when we get very high levels of dietary crude protein, so you wouldn't see these in forages very often, but when you're looking at values of sort of 25-30%, you would possibly start to see a negative impact on animal production, because the excretion of that excess protein has an energy cost to the animal as well. Another thing to bear in mind is that ruminants are notoriously inefficient in terms of their utilisation of dietary nitrogen, and only about 25% on average of the protein of the dietary nitrogen that's ingested by the animal is utilised, and the rest is excreted. And what's really key to making sure that that nitrogen use efficiency within the rumen is maximised is making sure there's sufficient energy to support microbial activity and the conversion of ingested nitrogen and energy to microbial protein. Particularly in dairy systems, and I think this is something that's going to come more to the fore over the next couple of years, as we're all being forced to refine and streamline and think about efficiency savings in all of our systems. The use of amino acid balancing in rations rather than purely focusing on protein is becoming increasingly common, I think. And methionine and lysine would be sort of the primary limiting amino acids within dietary rations. But this is more, it's more when you're looking at high production dairy cows that are going to have a higher demand for protein, and probably not so much so relevant to beef and sheep systems. So I've got a little diagram here that just highlights what I was saying about the complexity of the protein digestion in the rumen, and that the crude protein intake is going in and it's splitting off into rumen digestible and rumen undigestible, or bypass protein, and the different cycles that are going on there. And it's both the protein that bypasses the rumen and the protein from the microbes that provides what we would call metabolizable protein for the animal. I think most UK rationing systems now use metabolizable protein when they're generating diet formula, and there are various equations that can convert crude protein to metabolizable protein, but there's not perhaps a straightforward simple one that I could just highlight to you. But you can see the comparison in this table, and this is some recommended protein concentrations for dairy cows with different levels of production. But if we focus on the crude protein values, they're ranging from just under 15% to 19%, and we would see our grass forage analysis coming in at similar figures as well. And when you're looking at this kind of rationing, it's the whole diet that's important. So if your grass is not quite up to meeting crude protein demand, but you are feeding a supplement in the parlour, or you're feeding a creep feed or anything like that to your stock, it's the whole ration that needs to be considered. It's just a couple of tables here on sort of requirements for beef and lamb animals as well as dairy, and just highlighting that the ration guidelines would be looking at crude protein requirements for beef cattle at 12 to 16%. So easily, mostly met within what's provided in grazing grass samples. So thinking about the energy requirements, it's slightly easier, slightly easier for us to do some rough and ready calculations with for maintenance and production. These figures are massively influenced by sort of individual requirements. So your animal breed, animal size, the genetics, their genetic potentials for production, their health and the stage of growth, reproduction and lactation. So it's very similar to looking at the guidelines on the packet of crisps that say you should be eating this many calories a day, but we know there's so much individual variation between us that we've all got our own targets. But when we're looking at some rough calculations to give us a guide as to overall performance we should be looking for, we would say typically requirements for maintenance are 10% of body weight. That figure would be slightly higher in lambs, I think perhaps because they run around so much more and they're more active, they're more active in their growth, they're more rapid in their growth, so they have a higher requirement than older stock. In terms of production for daily gain or for sort of putting on body weight, we're looking 40 megajoules per kilogram of live weight gain, and for milk, on average 5.3 megajoules per litre, although that is influenced by milk composition. So there's a couple of calculator tools that I sent round by email at the start of the year, and I'm happy to run through these, sort of run through a couple of examples in these today if that's helpful to anyone. But what we've got in here are, on the left-hand side, the calculators are the ones that I sent round, and there's one for estimating milk from grass, live weight gain from grass for beef, and live weight gain from grass for growing lambs. The figures that are in red are quite easy to edit, so you would change the body weight of your stock. We have an allowance for activity in the milk from grass and the beef gain from grass in there. If you have a particularly long walk to the parlour or a particularly short walk to the parlour, you could put that up or down a bit. And then dry matter intake, so you can estimate that if you know what you're targeting your dry matter to be from your stock, it should give you a figure either of expected average daily gain or expected milk, or for the lamb one, these figures are in grams because your targets would tend to be in grams, smaller animals. I also sent a link round to something that's been produced by AFB for AgResearch, who are a levy board in Northern Ireland, and it's a slightly more complex version of this calculator for dairy animals, where you can put in supplementary feeding information, you can put in your specific, your bulk tank composition as well, to give you an indication, to give you a more accurate indication of the energy requirement for your stock milk production and the level of that requirement that you're able to meet through forage. And in terms of sort of what does this data, or what do these calculators support in terms of real terms? And again, I don't mean to be patronising with this slide because I think this will be familiar to everybody that's in this meeting. But if you've looked at those calculators and you've assessed, well, I've got X quality of grass, and based on what I know from my stock, I should be achieving Y production, but actually this individual animal is well under production, or my whole herd is not quite meeting target. There's a couple of key things to be thinking about, and highlighting the importance of regularly monitoring your production, which is easy for dairy cows, but with growing stock and your suckler herd and your breeding ewes, just making sure that regular monitoring both body condition score and weight so that you can see how they're doing. And then just thinking of, well, why might these stock not be meeting their targets? Is there a health issue that I haven't addressed? Is there an injury in this specific animal? Have I done a fecal egg count? What's the parasite burden? Is that having an impact? And then we can get on the whole whole herd level or the whole flock level, there will be things that you can't control. So there would have been issues probably for some animals last year in terms of heat stress during the heat wave. And then we can get into the more complicated issues of trace element and vitamin and mineral supply in the diet as well, to see if there was anything that could be causing an issue there. And I think key to remember when we're looking at troubleshooting performance is your vet or a nutritionist are really the experts to consult in this as well. But that was it for a very brief presentation from me, but I'm happy to run through any of those models or take any questions from anybody.